Yasmin, the floor is yours.
Thank you very much, Natasha, for this nice introduction. Hello, everybody. My name is Yasmin. We have already heard that. My colleague is Andreas Wirth. Andreas is today in Vienna, and I'm sitting in Salzburg in Austria. I would like to start this weather briefing with this world map overlaid with a water vapor satellite image. And before I come to this, please use the annotation tool that you find on the top of your screen to show everybody where you are right now. You can either just put an X there, or you put an S for sunshine, C for cloud, P for precipitation. And I will also try that with an, oh, okay. An S over Salzburg for sunny conditions here. Don't be shy. Okay, star means night. I don't think so. Okay, wow. Yeah, so we have so far only Europeans in this session. Okay, wow. Ireland is also here. Okay, great, wow. I know that weather is much more complex than only 3 parameters, but I had to keep it simple here. Okay, so we are spreading out a little bit now and have mainly cloudy or sunny conditions, but I haven't seen any precipitation so far. Doesn't matter, but maybe you already see that this water vapor image does not directly reflect the weather conditions. So when it's bright area, it doesn't mean that there is lots of fog. I will come to this in more detail quite soon, so thank you for annotating. I will have to delete your annotations now. Thank you very much. Okay, more sunshine coming in. Okay, thank you. So during this session, I would like to go from the top levels of the atmosphere to the bottom. So we will make our way through the atmosphere from above to the ground. And this is also why I begin with this water vapor channel. It's a very good mean for understanding the kinematics and basic processes of our atmosphere. So I'll just talk a little bit general about this water vapor channel. Satellites receive the radiation from the Earth in different wavelengths. And the 6.2 channel, the one that I'm showing here, receives the re-radiated signal from water vapor that lies in between, so lies somewhere in the atmosphere. So that means it's an absorption channel. The radiation in this channel therefore represents the temperature and the amount of water vapor in the middle and upper troposphere. Okay, to see if that works. Right. So here we have the weighting functions that show the relative vertical contribution of radiation in different infrared channels. And the two water vapor channels, 6.2 and 7.3, dominate the upper and middle troposphere. So here we are for the 6.2 channel in a level between 200 and 400 hectopascals. So it means we are looking at the upper levels of the troposphere. If there is moist air present in higher levels, in these levels here, the temperature of this layer is lower and the gray shade of the image is brighter. That means if we have bright colors on our image, we have moist areas, and dark colors mean dry areas. That's actually the basic outcome. So we can maybe indicate this: humid areas and dry areas. Where do the dry areas come from? So either from a very dry air throughout the troposphere, because maybe above a large desert, or, and this is more likely and much more often, from a dry stratospheric air mass. And therefore, the water vapor image reflects the vertical motion of air masses very well, because we know where we have these dark areas, we have subsidence from above, from stratospheric air. Well, that means, okay, so where we have darker areas, we have a downward motion, most likely. And if we go one step farther now, when we apply the concept of a constant PV along an isentropic surface, we can state that if the static stability, so the second term here, decreases because of subsidence, because the air gets lower, the first term here, the absolute vorticity, must increase. And it might sound a little bit complicated, but it's actually very easy and very useful, because now we can state that here in the darker area, we have a PV anomaly. So this is very useful for detecting, for example, early stages of cyclogenesis. All right. So now let's go to Europe. So usually in our weather briefing, we focus on the weather over Europe. So I will also now go to Europe and show again the water vapor image from this morning. So we have many interesting features over Europe. For example, first of all, okay, this well-pronounced frontal system over the Atlantic. I hope you can see my mouse. I guess that should be fine. Yeah, so we have a frontal system over here and even another one over there. We have a trough south of, here we have kind of a trough, and another trough probably here reaching down to southern Spain. Then we have also here some kind of darker area that might indicate a trough for cyclonic flow. And then maybe if we look to the smaller structures here, two small tiny eddies over the Mediterranean, probably this one and this one. So quite some features here that we will now have a closer look at. So first, I would like to overlay the PV height of 1.5. And according to the concept that I was talking before, the PV height should be higher where we have these darker spots. It should be higher. And yes, indeed, if we look very closely, we see that here this surface of this virtual topography reaches down to about 400, 500 hectopascal. So yes, here we have very clearly the subsidence in these darker spots. You can see it even here very nicely over Russia. Well, if we have, okay, so I have to switch the slide. It's not working now. Okay, I would like to make a little experiment with you and try to draw the streamlines like they would be found on a numerical weather prediction chart. I will just use my annotation tool. You don't have to do anything, but just trying it very, very roughly. So if we assume that here we have a trough and maybe here we have another trough, and okay, let's say there must also be some cyclonic curvature and also here over Russia. So that's actually the most simplest thing to start with. Here the small eddies, maybe like that, or even we can even surround it as a whole. So we have now indicated the cyclonic vorticity parts that we more or less know. If we, okay, I will just try to make them a little, just a few more to make it, to make it look more like a weather chart. Okay, something like this. If we connect now the lines, we automatically kind of get here the ridge. So the first trough over the Atlantic is followed by a ridge. Maybe it's something like this here. Here it's probably anticyclonically goes around here and then somehow to the east. And here I assume we have also this huge ridge over Europe. So don't judge me on my painting, but something like this it should be like. And now let's see what the ECMWF how they see it. Okay, I'm having trouble. Oh, I wanted to. Oh, I don't want to have them. Okay, so still, it's somehow the same pattern, and that's what I wanted to show, because I find it very fascinating that only from a satellite image, only from the water vapor, the higher levels, we can gain so much information about how the model even would look like. Okay, now it's again your turn, and my mouse is not working. Okay, there we go. Now you can take your annotation tool and try to find a jet stream or even the jet streams. We have already discussed a little bit, and having the geopotential overlaid, it might be a little help for you. Okay, there's already an arrow. Very nice. Yes. Okay, also something in the south. Thank you. Great. Okay. Yes, you're doing great. I'm waiting still for one other painting, one other arrow. Right, there we go. Okay. Yeah. So again, we can gain deeper knowledge about the current weather situation if we know that the jet streams are located along the thermal gradient of the polar front, and the maxima of the wind speed, so the jet streaks, can often be observed at the rear side of cold fronts. So if we say that here is a jet stream or jet streak, it might be at the rear side of a cold front, also ahead of warm fronts, or along the rear sides of upper level troughs. Might be here. Okay, I think first I have to delete. Thank you very much. That was really great. And now, next slide should give us the solution. So here we have the wind barbs at 300 hectopascal, and yes, indeed, you have had really good guesses, or actually probably you knew it. And so we have here very well pronounced jet streak, also here over Russia, here within this trough, and here the subtropical jet that you also have detected. Quite nice. Yes, also here we have a wind maximum. That's true. Okay, well, let's go on. From top to bottom, as I have promised, we are getting closer. This is the EUMETSAT RGB. It is a combined product of water vapor channels and infrared channels, and it's very useful for distinguishing MSs. So I have written here some keywords. Please go through them and try to put the shortcuts on the map where you expect the corresponding feature. So do you see frontal cloudiness or whatever? Take the first letter and put it wherever you like. Yes, you can either use the text tool, or you can just paint the letters. Yes, we have tropical EMAs, very nice. Fog lower stratus over Croatia. And polar air mass, nice. Okay, frontal cloudiness, yes. Right. Here I see F for fog within the front. I'm not so sure about that. Convective cells, yes, and convective cells here south of Turkey. Really nice. Okay, maybe more convection to find. Maybe a hurricane somewhere. Be creative. Okay, ground, snow, ice. We're here in Africa. We will check this. Okay, thank you very much. Well done. Let's quickly go through them. So frontal cloudiness, you have detected that very well. So we have here this kind of connection of different fronts with different frontal systems. So very clear frontal cloudiness. And also in this system, we have actually this core convection inside the cyclone. So convection can be seen here and also here, south of Turkey. That's also very nice convection, and also some convective cells over here. Yes, that's right. Ground, snow, and ice can actually not be seen by the air mass RGB. We will come to other products that are better for detection of snow and ice on the ground. Hurricane is not here. Thank you for not putting the H. Polar MS, yes, that's very nice here, the blue color, and tropical air mass is here in the south, this green ozone poor air mass. Fog and low stratus is very difficult to see with the air mass RGB. There are also better products for that. So I will continue. Okay, small hint here. If you feel really lost and insecure with this colorful image, I highly recommend the RGB quick guides of EUMeTrain that summarize on 2 pages the most important facts and how to use the RGB products in your daily life or everything behind it. So really good information, and Andreas will probably show you then on the website, on the EUMeTrain website. Okay, quickly have to delete again. This is the 24 hours microphysics RGB. I personally like it very much for my shift work because it can be used day and night, and it's really nice for detecting cloud physics, yeah, microphysics, and it's useful for different purposes, but also it has its limitations. But just quickly to show you, so we have here this red cloud that is a thick, cold ice cloud. Then we also see mid-level water cloud, thick water clouds. This is this yellowish, almost olive or orange color. We see even different ground characteristics, like land and sea is easy to distinguish. And we have lots of yellow color in this image. For example, here and here, also here and over here. And this yellow color means fog or low stratus. And here you can even divide between different shades of color, like if it goes more into pinkish, for example, I think here over Spain maybe, the droplets are bigger. Not to mix up with the yellowish bright color that we see here over Northern Africa. That is not fog or low stratus, that is a cold and sandy desert. Okay, again, for this product, of course, we have a quick guide that leads you through the or guides you through the how to use it, and yeah. Okay, just quickly to show you something that I have to deal quite often with. Here is Salzburg. So it shows we are we are somehow in the fog, but yeah, some valleys are still in the fog and some are outside, and you really nicely see this structures of the fog, how the fog goes into the valleys and how it lies in the flat areas. This is the fog RGB. It's quite nice for that purpose, also because it has a high resolution. But there is something else actually that I want to show you that's over here, the cyan color, which is not fog, although it has a very similar structure, but this is ice and snow on the mountains. So for this, it's very good to distinguish and also to detect snow and fog. Okay, yeah, we had this. And I want to conclude now with this day Natural Colours RGB and finally go to the very ground, showing you some webcams. Here we have Flensburg in northern Germany with cloudy conditions. Here, Salzburg, this is actually a webcam that looks down on my house somewhere. So you see we have some fog still there, but lots of sunshine above. Here in Portugal, it's a mix of low clouds and sunshine. In Norway, Trondheim, there is mostly cloudy weather, while here in the Pyrenees, it's very foggy, very low visibility. And finally in Sicily, Palermo, blue sky and lots of sunshine. So that's my part for now. Now, Andreas, it's your turn, and I will continue then with the weather outlook. Thank you very much.
Yeah, thank you. Thank you, Yasmin. Guess where I would like to be?
In the Pyrenees.
No, I would like to be in Sicily. So let me share my screen. Okay, so that's me. Welcome to the second part of the weather briefing. My name is Andreas Wirth. I start the presentation now, finding the right button. Yes, here it is. I'm working in Vienna, as Yasmin already told you, and I'm working more exactly in the remote sensing department, dealing with satellite data, radar data, and also with lightning data from time to time. So I have chosen a topic that came to me in the last week. A colleague from mine from the air traffic weather service called me and told me about an interesting situation. There was an incident. Nobody was hurt. Nothing happened. And he would like to know, or we discussed, what can satellite data and products like Yasmin showed us previously, what can they tell us and help maybe avoiding such a situation? So what happened exactly? It was 3 October, so early last month, that a plane from Vienna to Tenerife was starting in Vienna and had to return after encountering serious icing problems. You see that the plane was starting in Vienna and making its way along the Alps, not over the Alps, but on the northern side of the Alps, and finally turned 180 degrees over Salzburg, and yeah, came back on its way to Vienna and had to abolish the flight. It was a big plane. It was not a small plane. It was an Airbus A320. And the question is, what happened and why did it happen? And what can we do as meteorologists to inform pilots? And you will see that the answer is not that easy. So again, here, this is the flight track. You see that the plane started very steeply to reach an altitude of 34,000 feet. That is approximately 10.5 kilometers. Stayed there for about 7 minutes and then descended back to Vienna. And the pilots reported of severe icing what you see here is the visual ice inspector, that is a metal stick. And if there is severe icing from the window of the cockpit, the pilots can see the ice accumulation. And that's what happened. This is not an image of that case, but it must have been looking similar. That's what the pilots reported after the incident. And they also reported that they had problems with the turbines. There were some noise and some shaking of the turbines. So there was obviously also ice in the turbines, preventing them from a correct functioning. Well, these are the PIREPs, the reports the pilots issue when there is a severe icing event. And we had several icing reports on that day. There are 2 of them here. And what is interesting, and that does not happen very often, we have severe icing from a medium aircraft. So it's not a small, not a big one, it's medium aircraft, the Airbus A320, severe icing at an altitude of 350 to 250 hectopascal. That means very high up, which is quite unusual, I must say, because icing usually happens in at lower temperatures and not really at this high altitudes. So, but this is in agreement with other reports. They also reported that the icing happened in very high altitudes. So if I go back to this track, it must have happened somewhere, according to the PIREPs, in this area. So, but I think this case leaves open more questions than it can solve. So first, let's have a look at the synoptic situation on that day. You see the middle Europe. There are a lot of clouds in this air mass RGB. There's a cold front that arrives here, very nice one. But the icing appeared before the cold front, in the area where you see the high level clouds. And what I have drawn here with this red arrow is the warm conveyor belt. So that's moist, warm, humid air that is advected from the south and pushed towards the Alps, bringing some rain in the southern parts due to lifting, and also produces some lee cloudiness in the northern parts of the Alps. So this is a typical föhn situation, more or less. So these are the streamlines at a very high altitude, so it's 300 hectopascal, and you see that the wind is arriving from the south, and you have in north of the Alps the typical lee cloudiness that spans over large areas. So the whole northern part of Austria is covered by lee cloudiness, so thin ice clouds, more or less. But also parts of Germany and the Czech Republic is also covered by this lee cloudiness. So the front is just arriving. It's over the western part of Austria and not playing a significant role, except maybe that it triggers, of course, the warm conveyor belt. But the front itself is not involving in this situation. Let me clarify the 2 kinds of lee cloudiness or lee waves we can have. In general, we can have the energy dissipation in the vertical, or we can have the energy dissipation in the horizontal. If the waves propagate vertically, then we have a wave type like this in the top left image, vertically propagating wave. Usually the amplitude of the wave is not increasing with height, but is rather diminishing. If the situation is like in the bottom left image, then we have trapped lee waves. That means that the lee waves are trapped in a very stable environment. And in the satellite image, you can make this discrimination very easily. You can see in the bottom right image this typically cloud bands of not so high clouds, mainly water clouds, but you see this stripes. There is some high level cloudiness on top, but nevertheless you can see the typical form of the Lee clouds, this horizontal stripes. This is very typical for Lee waves, for trapped Lee waves. While in the upper right image, we have high ice clouds of vertically propagating waves. So in the case here, what we have are vertically propagating waves. So we have ice clouds mainly and high reaching ice clouds. Let's come to the products. The first products we can look at is the cloud microphysical information from the severe storm RGB. What you can see here is very typical. You can see north of the Alps in the region where the incident happened. The pirate was issued somewhere here, south of Linz, in this region. So it's a very yellow area, and yellow means small ice crystals. So small ice crystals normally affect the engines, the turbines of the plane. The effect is called high altitude ice crystal icing and leads to malfunction of the turbines. Not so much to the ice aggregation on the plane itself, on the airframe. This does not happen with ice crystals. Ice crystals are mainly dangerous for the turbines. So the pilots reported ice crystal, supercooled ice droplets, which clashed on the airframe and froze immediately. And that's what they saw on this stick I have previously shown. So this must have happened in a lower region where we have typically temperatures below -20 degrees. So what else can we see here? So we have the yellow color that is typical for CBs, for example, where we have very high reaching ice crystals, small ice crystals. But what we can see here is a green band here in the southern part, and also a little bit in the western part. A little bit greenish color, and green means supercooled water droplets. So why do we see that only in the southern part of this cloud? Well, this is probably the reason because the satellite is positioned over the equator, and what we see here is the little bit below on the edge of the cloud, of the ice clouds. We see a little bit what's happening below the ice cloud because of the viewing angle below the ice cloud. So obviously below this high ice cloud with small ice crystals, there must be some supercooled water, which caused in for the plane the icing with supercooled water droplets, but in a lower level. There's another product which seems quite interesting. This is the dust RGB, and Jasmin said she likes the 24-hour microphysic image very much, and I'm a fan of the dust RGB because you can see more structure of the clouds. What was yellow in the previous image now is red and black, and the reddish area shows you some thick ice clouds, while the black areas are typical for thin cirrus clouds. So we have at the beginning, the wind comes from the south, we have at the beginning some very thin cirrus clouds, and later on thicker clouds. This is as this image shows it. So more details of this ice cloud from the dust RGB. There is another RGB which is quite helpful for this situation, and it's very easy to interpret because it's sensible to the cloud phase information. Everything, Jasmin just showed it for snow and ice. Everything what is ice in the clouds is cyan, and everything what is water is white. And what you can see here are typical high-reaching ice clouds with thick ice layers, this very strong cyan. But in the region where we saw that the incident of the plane happened, we see both. We see some small ice clouds on top, and we have some transparency because they are not very, very thick. We see below some whitish colors, yeah, because the cyan here in this region, northern part of Austria, is not that strong than in the southern part where we have high-reaching ice crystals. So that's what we can see from RGB products. I think it is always essential to also see what the models give, because the models are very good nowadays, and we can make a cross-section using ePort and have a look in the vertical structure of these clouds. Of course, we can also have a look at the radar data, but unfortunately, I received some radar data from my colleague. They do not show much in this region where we have the icing report. Maybe we have some little bit higher reflectivities near Vienna and west of it. Yeah, this is the only thing from the radar. So the radar data is not very helpful. I think the NWP model data is very helpful for understanding the situation. So the cross-section I made here goes from Slovenia to the Czech Republic, so from south to north. And what we can see here in the cross-section is now the humidity field. We see the humidity in a level, high humidity, relative humidity in a level between 550, and 450 hectopascal. So in mid-atmospheric levels, high values of humidity. So this also confirms that in higher levels, so in cruising altitude where the plane was remaining for about 7 minutes before going down again back to Vienna, here in this level, at around 300 hectopascal, there is not much humidity. So icing probably did not occur at that level. Icing must have occurred in lower levels, so in the ascending flight path of the plane. This is what the model data shows us. If we go to the temperature, we see that between 550 and 450, we are here in the level of the temperature range. I wrote it here in the lower slide, between -6 and -18 degrees Celsius. And this is typically the region where most of the icing incidents happen. So supercooled water droplets can persist until -30 degrees, but there are not much of them. The colder the temperatures, the more ice crystals you will find. But for temperatures below zero, so -6 to -12, there you have the most chances and the highest chances for having supercooled water droplets, and not so much ice crystals. Only for temperatures which are below -12, -16, -18, depends, we have more ice crystals than supercooled water droplets. So in this region where we have high humidity, we have also the right temperature level that is necessary for severe icing. So the model data would help us very much in this situation. And another thing which is quite interesting, because this situation was a typically lee wave situation, what you see here is the vertical movement of the air. The mountains start in Slovenia, the Alps start in Slovenia, and where I have put the yellow, the blue arrow shows you the northern part of the Alps. We have a generation of waves, and in this case, it's a vertically propagating wave. This is clear from the model also. We have ascending movement of the air that flows over the Alps, vertically propagating waves until very high up, 200 hectopascal. So we are in the middle of ascending air. Ascending air means cooling, means also formation of ice and water droplets. So according to my colleagues from the airport, this is a very typical situation where we find icing, severe icing along the northern parts of the Alps, and well reflected in the model fields. What I can show you finally here is a product that is generated by my institute. It's a loop of 2 hours, almost 2 hours, and it has an algorithm that calculates the risk for high altitude ice crystal icing, HAIC. The algorithm was developed by the Netherlands Institute, used also by Météo France, and implemented in this product by my weather service. The red areas shows small ice crystals that are a threat for the engines, for the airplane engines. That means they aggregate on inside the engine and prevent them from correctly functioning, causing vibrations and reduce the power of the engine. So this is clearly red north of the Alps and moving to the north. There's another product, different algorithm, that shows you the risk for icing with supercooled water droplets. Unfortunately, this product has a big drawback. As you can see, if the cloud shows a massive ice or also some cirrus clouds on top of the supercooled water cloud, then it cannot see through or not really define if there is supercooled water or not, because the satellite, this is derived from MSG, only sees the upper layers. So white means undefined, while blue to red means minor risk to severe risk for supercooled water droplets. But in this case, and this is also the limitation of the product, and a very serious limitation, there is ice crystals on top of the clouds, and what's below is very difficult to see. So I think this was my last slide, and after this short presentation, I will give back to Yasmin, and I stop my sharing. Yasmin, are you here?
Yes, of course.
Okay, fine.
1 second, that I will share my screen again. Okay. That should be it. Okay, let's have a short outlook on the weather for the next days. Here we have temperature and pressure, then the equivalent potential temperature, wind gusts, this is precipitation, then we have the snow line and clouds. So let's go through the next days quite roughly, or let's maybe first begin with the situation today. Here is this huge system out on the Atlantic, while we have this huge high pressure area over Eastern Europe and this smaller trough here with maybe an upper level low over southern England. That will move to the east, while this trough from the Atlantic comes closer. We have here also this frontal system inside, connected with quite strong wind gusts, so that will probably be topic in probably France and England, Ireland on Wednesday, Thursday, when that hits the coast. Then very nicely on Thursday, coming in from the Atlantic, this system in the north that will bring precipitation, strong wind gusts, probably quite cold air, and especially change the weather or impact the weather in Northern Europe, while in the south this high pressure will still persist, and actually relatively warm air, warm and humid air mass here. And then finally on Sunday, still probably quite wet weather in the north over Great Britain. Not so much happening here over the south, where still this ridge that dominates over middle and southern Europe. Yes, and quite strong gusts here in the north. Hopefully it will not come so strong. I had also a look at the ECMWF extended range forecast. I want to show and share with you. So in this week, the medium range forecast says that Europe, the temperature, 2 meter temperature, divides Europe. So the east is relatively cooler, while the west is relatively warmer. This is for precipitation. Overall, it's a drier anomaly. So yeah, and then if we go forward week by week, we see that in general the signal weakens, but also this gradient between east and west dissolves a little bit, and then it turns out that Scandinavia, Northern Europe remains a little bit warmer. Here also still a little bit more precipitation. So generally in the north warmer, but elsewhere only little difference. But as I said, the signal is very weak then if we approach Christmas. So really hard to say if we have white Christmas all over Europe. It doesn't look like that, but of course I'm up for a surprise. So that's it now for my part, and I think I can give back to Natasha now. Thank you.
Thank you very much, Yasmin, and thank you, Andreas. We will now go to questions and answers. There are quite some in the Slido, so please, can we have the questions on the screen? Thank you. So we will go from top to bottom. The first question is, what features can be seen best in water vapor images and not so much in other satellite channels? This is a question for Yasmin, I guess. But
yes, okay, interesting. So what features can be seen in water vapor images and not in other satellites? So as the water vapor channel looks at the higher levels, it can best detect areas, for example, with PV anomalies or early cyclogenesis, or even jet streams because of the darker stripes, so where the jet stream has the subsiding side. So that's something that cannot be seen by any other satellite channel, or really hard only. So that's the big advantage. Maybe also, I'm thinking of something else. Maybe Andreas, you have also another idea. Generally, everything that has to do with dynamics and kinematics that happen up there. So, yeah.
okay.
Anything to add, Andreas?
No, that's perfect.
Okay.
Okay. So the next question, is there an archive of these satellite products? Are they available as data files as well as imagery? Many thanks.
Well, I shall answer this. The images Yasmin showed are available in ePort, and the archive goes back until 2018, so 2 years. So what is the last two images I showed, the HIC and the supercooled water droplet, there's no archive for that shows you visible images, but we have an archive of the data. Both products are not yet operational. These will become part of the nowcasting stuff, are not operational yet.
So maybe I can add that all satellite data are available in the EUMETSAT archive, but unfortunately not in the image format, just as data format. So if anybody can, everybody can access the data, the archive data, but they are not available as imagery. Okay, let's go to another question. Which kind of satellite data source is used to calculate water vapor 6.2?
I'm not sure if I understand the question right. Which kind of satellite data source? what is meant by this?
Okay, so maybe there is a misunderstanding. The 6.2 is a channel that a satellite directly measures. So the satellite directly measures radiation in 6.2 channels, and the image is what comes directly from the satellite. It is not calculated, it is just transferred from measured radiances into, let's say, temperatures, and showed in the gray shades in the image. So yes, I think that was a misunderstanding probably. Okay,
thank you, Natasha.
So, yeah. So the next question is, I guess, for Andreas. Which layer does it refers the height and the SC?
Yes, one of the drawbacks of the two products, there is no level that corresponds to the colors. But if you use cloud top temperature and height from the nowcasting soft, you can refer it to the appropriate height. So you have to use another product to see which height is meant. In general, the satellite only sees the cloud tops, and the cloud top temperature and height also sees the cloud tops and gives the height of the cloud tops. So if you use the other product, you can refer it to a height.
Mm-hmm. Thank you. So, Yasmin, thanks for showing water vapor image in the beginning. Do you ever use water vapor 7.3 in your analysis?
Ah, that's interesting. Not so often, actually, to be honest, but sometimes it's interesting not only to overlay the geopotential on 300 hectopascal, as I have shown, but also to go to other levels, like 400, 500, whatever, hectopascals, and see the differences and see how other levels look like on the geopotential chart. And for that purpose, it would be, or it is also useful to look at 7.3 micrometers because it looks a bit deeper, a bit lower into the atmosphere. So yes, for that purpose, I do, but mostly to just have a look at the water vapor, I use 6.2.
Good. And so, Andreas, is convection RGB the best to look into particle size?
I don't know. It's a good RGB for seeing the particle size. If it's the best, generally all RGBs that use either 3.9 or 1.6 are good for particle size. And this RGB, the convection RGB, uses both channels. So yes, it's one of the best. I don't know if it's the best, but it's a good thing to use it for that purpose.
I agree, it's a good one. Okay, and the last question we have in Slido, again for you, Andreas, which satellite channels does the HAIC
high altitude ice crystal icing? Yes, yes. I should have prepared better for that question. So I suppose, I mean, it uses the available channels from MSG, of course. And since it's a product that detects ice, that it detects particle size, it must use the microphysical channels of the satellite. Apart from this, if it also uses temperature channels like 10.8, I don't know. Yeah. Sorry, but I cannot give a fulfilling answer to that.
Okay, thank you. We have another question in the text chat. The question is, why 700 millibar and surface maps are not used for forecast analysis, especially when the 500 millibar and surface are piled up? The intensity of the phenomenon is definitely higher. Why don't you use boundary layer analysis in forecast analysis and its ensemble and models? This is the question from the text chat.
And I see an answer from Vesa. Maybe
yes,
we can also read this.
So the Vesa answered, Behrus, in my forecasting, I used to use 500 hectopascal for upper level, non-divergent flow analysis, and it was the basic starting point for checking the flow. The 700 hectopascal in non-mountainous regions was our choice for monitoring the moisture and the low levels we use more for actual surface frontal analysis. It may be that the forecasters in various geographical locations have a preference for different levels. I can add to that maybe that Yasmin just did not use everything she would use in an everyday analysis. She just wanted to show some example analysis.
Yes.
That's also the point.
Exactly.
Yeah. Okay, so these were the questions. Thank you both for the answers. We will move to the last part of today's short course. That will be the introduction of the EUMeTrain project. So Andreas, who is also the EUMeTrain project manager, will tell you more about it. You can still place questions in Slido if you have some. And also before the end of the session, please tell us your opinion about this short course by filling up the evaluation that is also available in Slido. So Andreas, please.
Yes, thank you, Natasha. So this weather briefing usually takes half an hour. We are now with 57 minutes, largely over that time, and I will not take much of your time anymore. I just want to give you some appetizer when you go to the EUMeTrain page, and I want to make some advertisement of the page. By the way, we are in the course of changing the page, and we will get a new design early next year probably. But right now, what can you find on the page? Maybe something I would really recommend to you is the monthly weather briefings. For those of you who are new to that and you subscribe to that, you just click on join if you want to just join once and look at it, or you want to be reminded that there is a weather briefing by a mail, then you can subscribe. So just check here if you're interested in the monthly weather briefings. That weather briefing is, by the way, done by different institutes, all members of the EUMeTrain consortium. So it's not always ZAMG, it's sometimes the Portuguese, sometimes it's Croatia, Hungary. So there are some institutes that are sharing the work. So it's always a different region of Europe that is shown. So typically Austria was shown this time because that's our point of interest, but the Portuguese Institute will rather have a look on the Atlantic or on the western part of Europe. So it's always a bit different. What else? Very important, what we do is shown here, the announcement of courses and the announcements of past publications, recent publications. Is shown on the left side, and on the right side the courses that we have and where you can get more information and subscribe to the course if you are interested. So let's give you the main information on this page. We have resources, we have this is all our data products that we can give to you if you want to have more information on any topic related to satellite meteorology. Yeah, let's have a short look in it. So this is our gallery. All the products, all the training tools are here. This goes from interactive learning modules to webcasts. Everything can be seen here. You just need maybe some speakers. If you go here to conveyor belts, you can have either the lecture slides or you can go directly to the webcast. Then it loads and yeah, okay, that's my voice again. Okay, that's something I recently have done for another course. Let's go back. So just go there, look in the categories, and see if there's some material that you are interested in. If you're looking for a certain feature, you may find it here. Unfortunately, there's no search area. This will be available in the next version of the homepage. Well, ePort is something where you can find the data. There are two versions of ePort. There's one which is simpler and Java-based, but contains all the images, all the numerical fields. Every 3 hours you have a satellite image with the model fields. You can have your analysis. There's MSG in this image, but if you use ePort Pro, and this is the other one, You have also ePort Pro here. It is a very recent tool that shows you more satellites, not only MSG, but also goes east, goes west, so goes 16, goes 17, Himawari if you are interested in the Japanese satellite, and also METOP. You have much more information than the simple ePort that was shown in the previous display. So let's go back. That was a bit too fast, too far. We have some manuals if you're interested in learning, teaching material. We have a satellite synoptic manual that is known by many of you, I suppose. We have quick guides. I go there. So if you're interested in RGBs, if you use them daily in your daily work, but you forgot, for example, what Yasmin was showing, the 24-hour RGB, and you forgot what is the yellow color here. So yellow is 1, or yellow can also be 6. And here you have a short interpretation on the colors. So also the limits and the benefits of this RGB, the background, and so on. Quick information means two pages, and that doesn't take you longer than, let's say, 10 minutes to read it, and you have the most information that you need. Yeah, we have also other quick guides also in preparation for MTG, the new channels. So if you're interested to the things that will come up end of, I don't know, 23, so in 3 years with MTG, then you will have different channels, will have different RGBs. Go there and have a look at the new possibilities that will be offered to you once MTG is in place. RGBs from other satellites like the GO satellites or the Himawari satellites, you can find them here. Very short, not to steal your time. If you want to have a look on past courses, you can go here. If you want to go back to past event weeks, you go on this page. An event week is a week where you have lots of presentations on the topic. We had this year YASI Level 2 product event week that was organized by the Hungarian Met Service together with EUMETSAT, and there are lots of presentations that you can hear if you have time. If you're interested in these different topics, then go there and listen to the presenters. We have some image gallery that shows you satellite and clouds. This is just in the processing of being made, but it's something similar than Yasmin showed for Sicily. Nice beach and no clouds like here, for example, and then you have the satellite image for the region. Yeah, okay, it's the contrary in northern Germany, so I'm lucky I'm not there. Well, let's go back, and this is something that will become more and more important, is the MTG training. So you all will have to deal sooner or later with MTG data, and we try to collect here information on MTG. So you have already seen information on MTG in the quick guides, but we try to collect them here on this page. And sorry, here case studies and webcasts. So all material that we can provide and that are related to MTG is in this section of the page. Yeah. So this is just the beginning. We have 3 more years until MTG will be operational. So please go there from time to time and see what's new, and don't wait for the satellite to be launched and sending images. You can prepare much in advance by looking at the future possibilities that the new satellite will offer to you. So I think this was a very quick way through. There are many more things to see and to listen to. Go there. I encourage you to, if you have some free time during your shifts or whenever, go there and just get some information. So thank you. Back to Natasha.
Thank you, Andreas, and thank you again, Yasmin. I'm sure many of our participants will use it if they already didn't. Thank you all for listening. If you missed something, the recording of the whole session will be available on the EUMeTrain website under Weather Briefings. Have a nice afternoon, and we hope to see you in some of the next short courses or some of the next Weather Briefings. Bye all.
Bye-bye.
Bye.
Bye-bye, everybody.